Okay, so let's unpack this. Imagine you're standing right there at a pivotal moment in science where these huge questions about what matter is and how light really works, well, they were about to be completely turned on their head. Today, we're taking you back to 1902 to a really groundbreaking Nobel lecture given by Hendrik A. Lorentz. We're diving deep into Lorentz's own words from that lecture, the theory of electrons and the propagation of light. That's our core source material here. This deep dive is basically your shortcut to understanding these foundational ideas that, bridged light, electricity, magnetism, and really laid the intellectual groundwork for so much of modern physics.
Yeah, and what's truly fascinating here is how Lorentz, with incredible foresight, really masterfully weaves together these experimental observations and the emerging theoretical concepts, especially Peter Zeeman's incredible discovery. He uses that to introduce us to this revolutionary idea of the electron and also this persistent but, well, increasingly problematic puzzle of the ether. So our mission today is to sort of uncover how these ideas, which were totally cutting edge back then, fundamentally reshaped how we understand light and matter.
Right. And just for a bit of historical context, Lorentz was actually delivering this lecture because his co-recipient, Peter Zeeman, was unfortunately ill. So Lorentz kind of took on the task of discussing the general theory, and he brilliantly built upon Zeeman's specific and really quite incredible experimental breakthrough. It really speaks to their collaboration.
Okay, so before Lorentz and Zeeman, scientists sort of knew that magnetic fields could influence light. Faraday, for instance, he'd shown it could rotate polarized light. And Kerr found similar effects on reflection from magnets. But the real puzzle, the one that kind of cracked open the atom, that started when Zeeman took it a crucial step further.
Precisely. Zeeman showed that a magnetic field doesn't just affect light propagation or reflection, but it fundamentally alters its origin, the actual process of light emission. Picture this. You take a light source, maybe a colored flame or an electric spark, put it between the poles of a magnet, and its spectral lines split. And this wasn't just some curious little observation. For Lorentz, it was like a profound window right into the atom itself. Wow. It's just astounding to think that from watching something as seemingly abstract as spectral lines splitting, they could figure out the fundamental ratio of an electron's charge to its mass. So Zeeman's key observation was this. A single, sharp spectral line, when you look at it in a powerful magnetic field, it didn't just shift or blur, it dramatically split, often into like a distinct triplet, but sometimes even more complex patterns. So what did that immediate visual clue tell Lorentz about the fundamental nature of how light gets emitted?
Well, this was a direct signal. It meant light wasn't just some wave coming from an unknown source. No, it was tied to specific charged internal vibrators inside matter. It was really the first solid experimental hint at the subatomic world. It suggested that something inside the atom emitting the light was being directly influenced by magnetic forces. And whatever those internal components were, they had to be charged.
Okay, right. So Lorentz explains his theory, imagines the physical world having these three core bits. Ordinary, tangible matter, he called it ponderable substances, then electrons, and the ether. But before we get to electrons, this ether idea, it feels so, pervasive, but really elusive. How did scientists back then truly think about something that filled everything but was seemingly invisible and untouchable?
The ether was, well, for a long time, it was the only coherent answer they had to that fundamental question. How does light travel through empty space? It was conceived as this universal medium, the bearer of light, you could say, and all electromagnetic stuff played out on this stage. Now, early thinkers like Edlund had some hypotheses trying to connect ether to electric fluid, but it was really Maxwell and Hertz who cemented our modern understanding of light's connection to electricity.
Right, Maxwell had already done this beautiful unification of electricity and magnetism, showing light itself was an electromagnetic wave, this rapid dance of electrical and magnetic forces. And then Hertz brilliantly confirmed it experimentally, showing that radio waves and light were fundamentally the same thing, just different wavelengths. He essentially proved Maxwell's elegant equations worked in practice.
Exactly, and that unification was monumental. It meant there was this vast spectrum of electromagnetic waves out there, everything from Hertzian rays of electrical force, which became wireless telegraphy, to dark thermal rays, ultraviolet, even X-rays. It was a grand conceptual unification of things that seemed totally separate before, all transmitted through this elusive ether, seen as the omnipresent stage for these cosmic vibrations.
But, okay, despite its crucial theoretical role, the ether itself stayed this profound mystery. What was it, physically? Like an elastic medium, a frictionless fluid, some kind of jelly? And maybe more importantly, how could you actually test its properties or even detect it?
Experiments to detect its movement or drag were absolutely crucial. Scientists imagined scenarios, right? What if the Earth, zipping around the sun way faster than an express train, was pushing the ether aside like a ship cutting through water? You'd expect some measurable effect. Think about a barometer the ether must pass through the glass, supposedly. Or astronomical observations of stellar aberration, that apparent shift in star positions because of Earth's motion.
But all these really clever, crucial experiments,
Yep.
from barometers to looking at stars, they consistently gave a negative answer. The ether didn't seem to move with matter. That must have been a huge frustration, like a real scientific crisis point, wouldn't you say? How did Lorentz and his colleagues even grapple with that seemingly impossible contradiction?
Oh, it was definitely a deep intellectual struggle. It questioned the very foundations of their physics. Fresnel's hypothesis, which was still largely the accepted view at the time, proposed this radical idea. The entire Earth is completely permeable to the ether and doesn't drag it at all, which leads to a pretty profound conclusion. If even something as dense as Earth doesn't drag the ether, then individual molecules, maybe even atoms, must also be permeable. It suggests an atom itself might just be a kind of local modification of the omnipresent ether, shifting around without the ether itself changing position. So the ether is fundamentally distinct from what Lorentz called ponderable matter.
Okay, so we have light as electromagnetic waves traveling through this weird stationary ether, but we know light behaves differently in stuff like glass or water compared to empty space. It slows down, it refracts, different colors bend at different angles. How does that happen if the ether isn't dragged by the matter? That implies something within the matter itself is interacting with the light, right?
Exactly. Lorentz, building on some older theories, proposed that these ponderable substances contain tiny particles that are set in motion by the light vibrations. And here's the critical revolutionary insight. If these particles are moved by electrical forces, and light, being an electromagnetic wave, definitely exerts electrical forces, then these particles must be electrically charged. That was the conceptual bridge. Okay, and these small charged particles, these are what we now call electrons, and the name John Stoney introduced. So you can sort of picture tiny charged dust motes, but instead of just floating around, they're bound inside the glass or water, vibrating around their equilibrium positions. What's the historical context for this idea of charged subatomic particles? Was it truly just out of the blue? Not entirely out of the blue, no. The idea of charged particles wasn't totally new. I mean, electrolysis, the whole basis of electrochemistry, was already explained by assigning charges to atoms in a solution. And Arrhenius had this bold idea of progressive dissociation, where molecules split into charged ions when dissolved. That was foundational too. So the concept of charge as a fundamental property of matter was kind of floating around. But Lorentz's genius was really in applying it specifically to the interaction between light and matter.
Right, and by applying the sophisticated tools of electromagnetism, Lorentz actually derived formulas for things like light velocity and refractive indices. These formulas showed a dependence not just on the light's color, its vibration period, but crucially on the nature and the number of these electrons within the substance. This formula, which Lorentz and Copenhagen also discovered, it didn't just model what they saw, it showed that these electrons have mass, and importantly, they don't follow all light vibrations equally easily. That explained why different colors refract differently.
And what's more, this formula also elegantly linked how light refracts to the chemical composition, specifically to the number of atoms of elements like carbon or hydrogen, not really how they were bonded together. And this pointed towards a monumental conclusion. The electron, and whatever it's bound to, must reside within a single atom, which led to the bombshell realization that electrons have to be much smaller than atoms.
That was a genuine bombshell. Yeah, for centuries, atoms were thought to be indivisible, right? The fundamental, unchanging building blocks. Lorentz's work, beautifully backed up by J.J. Thomson's independent findings with cathode rays, just shattered that view. It revealed this complex internal structure, a whole universe inside each atom. So, okay, with the electron theory now in place, the Zeeman effect, that subtle splitting of spectral lines, finally made perfect sense. Lorentz argued that it's electrons vibrating within these incandescent atoms that actually emit the light. They act like minute Hertzian vibrators, he called them.
Exactly. And the very force causing the changes in these electron vibrations when you put them in a magnetic field. It's the same kind of force Ørsted discovered way back when he saw a current affect a compass needle. The detailed analysis of the Zeeman effect showed it's specifically the negative electrons that oscillate. This wasn't just theory anymore. It was direct experimental confirmation of the electron's existence and its properties.
And here's where the numerical precision gets truly mind-boggling. From the spacing, the actual distance between those split spectral lines, they could precisely deduce the ratio of an electron's charge to its mass. What did that ratio, when they finally pinned it down, tell them about this new particle?
Well, combining Zeeman's experiments with data from color dispersion, the electron's charge was estimated to be pretty similar to an electrolytic ion, a charged atom in solution. But critically, its mass was tiny, about 1/800th the mass of a hydrogen atom. J.J. Thomson confirmed this result too. This meant the atom itself absolutely had to be a composite structure containing these much, much smaller electrons. It validated the whole idea of subatomic particles. And just to give you a feel for the scale, Lorentz pointed out, if you put just a millionth of a milligram's worth of surplus electrons on two iron spheres, say a meter across and 10 meters apart, they'd repel each other with a force of over 80,000 kilograms. That's an immense force from an incredibly tiny amount of actual stuff.
But the universe, as it tends to do, isn't always simple. While the theory worked beautifully for triplets, lots of spectral lines actually split into more than 3 components. This was a stumbling block, as Lorentz called it, a real challenge to the simple electron theory that scientists had to confront. It suggests a deeper layer of complexity, doesn't it?
It absolutely did. Lorentz, always pushing the theoretical edge, deduced something quite subtle. He figured if a spectral line splits into, say, 6 components, then even before you apply the magnetic field, the incandescent atom must already have 6 distinct vibration patterns, all happening at the same frequency. The magnetic field then just sort of pushes apart these pre-existing patterns, making their slightly different frequencies visible. This implied a far more complex internal structure for atoms, like an elastic body capable of many different resonant vibrations. It hinted at this intricate dance happening within the atom itself.
Yeah, Lorentz was convinced that real progress would come from studying all the lines of a chemical element, not just picking one, and understanding their regular relationships. Researchers like Rydberg, Kaiser, Runge, Paschen, and others were already working on this, finding patterns. The ultimate goal was nothing less than a unified theory of light emission and spectrostructure, kind of like a periodic table, but for light itself. So, okay, what does this all mean for the bigger picture then? This electron theory wasn't just about explaining light. It opened up what Lorentz called an enormous field of study across physics and maybe even beyond.
Right, if we connect this to the bigger picture, the electron hypothesis promised, as Lorentz put it, a rich harvest across physics. It could potentially explain the conductivity of metals, thermoelectricity, magnetism, heat radiation, even the properties of crystals. And even more profoundly, if bodies actually change dimensions when moving through the ether, which optical experiments like Michelson-Morley were strongly suggesting. It hints that maybe molecular forces are also electromagnetic at their core. This raises the really audacious possibility that maybe material particles are actually composed of electrons, or at least that their charges are central to all the forces holding molecules together.
Wow, so this led to this really ambitious hope that the electron hypothesis would lead to a general theory embracing many aspects of physics and also of chemistry, culminating in an electrochemical theory of matter, a grand vision that thinkers like Berzelius had sort of dimly foreseen much earlier. This was truly a paradigm shift in how we understood the very building blocks of the universe, just fundamental. So from just looking at the subtle splitting of a spectral line in a magnetic field, we've journeyed into this world where light is fundamentally electrical, matter is made of tiny charged particles, and even the very concept of mass starts to blur with energy. What an incredible intellectual ride through the foundations of modern physics.
Absolutely. Lorentz's Nobel lecture is really a masterclass in how the foundational theory can unify observations that seem completely disparate and just propel an entire field forward. The electron, this idea that was just solidifying right at the turn of the 20th century, it profoundly reshaped our understanding of light, electricity, magnetism, the very nature of matter, and it paved the way for the quantum revolution and, of course, Einstein's relativity. It just shows the power of theoretical elegance combined with rigorous experimental evidence.
So what does all this mean for your understanding of the universe today? Consider this for a moment. If an electron's mass can actually change based on its speed, which was a truly revolutionary idea that upended Newtonian physics and directly foreshadowed Einstein, and if atoms are, as Lorentz proposed, essentially modifications of the omnipresent ether, how much of what we perceive as solid stuff is truly static, and how much is just a beautifully complex, energetic dance of invisible forces and particles? It really makes you wonder what other apparent truths out there are still just waiting to be redefined, doesn't it?